guess we've officially started fall. The equinox was yesterday. Although I don't really see that as like fall. To me is like September, October, November. Winter is December, January, February. Spring is like March, April, May. Summer is June, July, August. To me.
Fall is when Starbucks has pumpkin spice.
Oh yeah?
Winter is when Starbucks has the peppermint mocha. I don't know about
Spring.
That fucking unicorn shit.
It's good to hear that. That's gonna be on Lalim or on YouTube now. Unicorn feces. It's what describes springtime.
Oh. Whoops.
Could be Lucky Charms, perhaps, or I don't know, Easter. Well, there's Christmas decorations in Costco now. Not even Halloween yet. Jeez, class hasn't officially started, so 2 more minutes. But I always thought, like, I know June is supposedly spring, but I always thought it was summer. For me, at least. I don't know. What do you guys think? When does the seasons work for you? I also think in school years, like, to me, January 1st is not like the new year. It's like August 1st is more like the new year for me. I don't know if you guys feel that way. Used to be July. I think in ancient times of July 1st. Oh, it's 3 o'clock now. All right, so I was asked about the schedule. Don't worry, we're fine for schedule. October 9th is the first test, and that covers chapters 1 through 5. So we're going to finish up with chapter 4. Actually, I'm going to go over it in a little bit more painstakingly detail, chapter 4, because this is a lot of the stuff that students get stuck on. At least, especially the ones that didn't have high school in chemistry, or the ones that had really crappy high school chemistry. So this is kind of the more important stuff. Things like converting mass to moles and doing limiting reagent, these types of things. So this is the problem we left last week. So we have this equation, this balance equation, 2 nitrogen monoxides plus 5 hydrogens yields 2 ammonias and 2 waters. Starting with 86.3 grams of nitrogen monoxide and 25.6 grams of hydrogen, what is the theoretical yield of ammonia in grams of ammonia? And the way that you do this problem is that you calculate for both, and then you pick whatever's the lowest. So what produces the lowest is the limiting reagents. So starting with 86.3 grams of nitrogen monoxide and doing the molecular weights. So nitrogen is 14, oxygen is 16, 14 plus 16 is 30. And so convert to moles nitrogen monoxide. And the step here, there's a 2 to 2 ratio between them, then molecular weight of ammonia. Nitrogen is 14, hydrogen is 1, 14 plus 3 times 1 is 17. And then hydrogen, same thing, mole hydrogen, 2 grams of hydrogen, new step. The ratio, the balanced chemical equation, 2 moles of ammonia to 5 moles of hydrogen, so this here, and then the same molecular weight, and we get 48.9 grams of ammonia based off of the nitrogen monoxide as the limiting reagent. So questions on how to do this at all? Okay, so here is your turn. 100 grams of oxygen and 100 grams of hydrogen react, how much water will form? And I've gone ahead and done it for hydrogen for you guys. And here's the hints. Here's the balanced chemical equation. 2 hydrogens plus oxygen makes 2 waters. Oxygen is 32 grams per mole, hydrogen is 2 grams per mole, water is 18 grams per mole. And notice also when you do these dimensional analyses that right here it says the gram hydrogen is in the numerator, then the gram hydrogen over here is in the denominator, and the units cancel out. So be sure to place that such the units cancel out. So have at it. Is anybody completely confused, doesn't know where to start? Raise your hand. Okay. Are there other ones?
Victoria?
Victoria.
She has a kid. So some days,
Okay.
like this time, she has trouble.
Okay.
Oh, they're grandkids.
Well, that's quiet. No, I mean, no, I don't mean that. I don't mean that.
No, the way you said it was so fun.
Oh, and feel free to talk amongst yourselves, of course. You following, Michael? You're looking good.
I'm
Stroking your beard. You know, contemplating.
I don't know why I did that like that, but it broken into quarters. I think it was last night. I was
Okay,
doing
wait, did we do this last time?
Yeah. We stopped here. We didn't finish it. But I'm trying to.
I'm already up.
Doritos, and looking
Oh, you have more than one subject to
This is all kind of
more.
I just lit up, so I do my work.
You started working?
My
Like,
this is the last.
Yeah, you got it. Yeah, you got it.
well, no, you did it for a week. You had to wait
You actually
24
did?
hours before you can write it out again. But if I was like, you know, at night, I'm for sure
You're still working. Yeah, you get.
leaving all the time.
Yeah, you got it. Go ahead. Oh, Oscar? Okay. So, 100 grams is good. Right? 100 grams is good. And now you gotta, so the idea is that the units down again, you want grams of water on the right.
Yeah, I
So,
had a Bud Light.
we just start with mass.
And then when you run a Bud Light over there, because mass has like so many times.
Then you have moles height, and you do this by like the way height is 1 gram per mole. So,
We don't have it for now.
so 2 H's is 2 grams.
I'm still on top of it.
And now we'll work on the balancing equation.
Have you tried it?
2, 2, 2. Like that. So 2 here, 2 there is where you get this stuff. Yeah. And then step is also more than water. So 2 times 1, hydrogen, and 16 drops of syrup. 2 plus 6. And then you go to the mole of water. Yeah, this is the same thing as multiplied by 1. So 24 hours is a 24 hours average, that's 1. And then the units just cancel one.
Can we just do this? That's so cute.
Yeah, okay. That's the right answer. Yeah. It's gonna be 2 finding water, so that'll be 1 mole. The balance equation. About 1 to
Because 16 is the atomic mass.
Which one?
One
was easy.
Yeah.
If you have your own
Crap.
Well, it's not really
version.
it's just the procedure. Carol will. You got it. Okay, yeah, you're good. Yeah, that's okay, good. You suck.
Where do you get 2 more H2O from?
So,
2 H2Os from the middle.
you suck, I need to know.
And where do you get the 2 1?
So if you look at the periodic table,
Just it's given.
oxygen is
Well, there's 2 of these and 2 of those.
so we'll row 2. 2 times 16
Oh, okay.
for oxygen is 32. Is 2 times the number of oxygen.
Yeah, the text message saying it's like for this one. Here's
So that's what that picture is.
one.
And water, hydrogen is 1, so 2 times 1 plus 16 is 8. Hydrogen, 2 times 1 is 2. And then you notice that the grams, 2 are here, moles are 2 are here, moles 1 are here, so they cancel out as they go across. Yeah, this step here is probably the most difficult. This is from the balanced chemical equation. It's a 1 to 2 ratio here. 1. So 1 here. Do you have any questions? Okay. Do you have any questions? Or? Okay. How you guys doing? That's right. Yeah. Limiting reagent.
Because it's the smallest.
Yeah. So do you have any questions?
So you get this by multiplying oxygen's atomic mass by 2.
Yep.
Because there's 2 oxygens. And then this one is the atomic mass of hydrogen. How come it's not times 4 since there's a 2
2.
and 2?
That's just the balanced chemical equation. Hydrogen itself is just 2.
Okay.
Yeah.
And then there's 2 H2Os, so that's oxygen's atomic mass plus hydrogen's
Times 2.
atomic mass times 2. And then the 1 mole oxygen, what is this 1 times?
So the balanced chemical equation. So you have 1, 2, 2 there.
This is, you're going from grams of oxygen to
Um,
moles of oxygen. So it's atomic mass per mole.
Does changing it to mole, oh, it's atomic mass per mole. So whenever you use a mole, you have to use the atomic mass of that one
Well, if you're changing from mass to moles,
What else would you change?
moles to moles, like you do like in this step here. You're going like in this in your step, this one here, because you're changing from moles water to moles oxygen, or I was saying to moles oxygen.
And that one's that's where the 2
Yeah.
to 1.
Yeah.
Do you know any of the other chemistry teachers on the island?
I know some people in high school, and I know.
Do you know Mr. Picciotto? He was my chemistry teacher junior year. What about Kincaid?
Okay, no, I don't know. Kincaid doesn't have a chemistry. Well, they didn't last year.
Do you know Mrs. Anchetto?
Isn't it Kathy?
So,
She
yeah.
did there's a guy named Mike. I forget the name of the teacher, but Mike is the lower level, and then there's the AP.
Yeah, Anchetto, probably. I was my AP chemistry teacher in high school too.
Yeah.
But yeah,
She's good.
I never took chemistry in
She,
high school, that explains it, and so much more than I do.
there's a mnemonic, I think. I don't know if it's a mnemonic, but it's grams to moles, 50 grams.
Oh, okay.
Right. So you're going from grams to moles to moles to grams.
Is it like that every time?
No.
But it helps
No, it could never be that simple.
Yeah,
It's chemistry, of course.
that's all I
Do you have any specific questions?
It's slowly starting to make sense.
Well, good. So it's like here. Okay, so for this problem here, start with the oxygen, you get 112.5 grams of water. For the hydrogen, you get 900 grams of water. Which one do you pick? You pick the lower one. And also, when you look at this problem, you can already discount 900 grams because you start with 100 grams of reactant, or 100 and 100, so you have 200 grams reactant. How can you have 900 grams products, right? You have to still have matter conserved. So answer choice D is definitely the wrong answer. And since you have the reactants and both reactants the elements are in the product, it's unlikely that you're going to go under 100. So A is out too, so if you choose between B and C, it would be unlikely that it would just completely add together. So really B is probably the only answer that would be feasible from this if you just use simple logic kind of going through. But okay, anybody have any questions about this before we move on? Okay, so next thing we're going to talk about is percent yield. So we can obtain titanium from its metal using this following equation. And here's the equation. So titanium dioxide, also known as rutile, plus carbon makes titanium and carbon monoxide. So this is another case where the book is absolutely correct. It's not in fantasy land anymore. This is how we get metals. So the way we get metals, we crack ore, and we typically use carbon to reduce the metal. So metallurgy is an old science. We originally got it with just campfires. You can get copper and lead from just using a campfire. And they found this, and you can so take copper ore and you can heat it up in a campfire, and then the carbon that's in the wood will reduce it and get the metal. The same thing with lead. So galena, lead ore, it's a real shiny black rock. And if you find it, so like the settlers in like the United States, or I guess the greater America region, they could find galena on the ground, and if you throw it into your campfire at night, the heat from the fire and the carbon from the fire can reduce the lead, and you can get lead slugs. Like the next morning when they wake up, they would find lead slugs in the ash of their fire. And this was important because then you could take that lead and you can melt it on a fire too, and you can make musket balls. So if you got gunpowder and you could find galena, you could make your own ammo out in the just walking around the forest gathering rocks. So and so if you have you ever seen the show Ancient Aliens? I've been watching that recently. It's on Netflix now. I love that show. It's so stupid. I love it. You know, but like the idea where there's like, oh, there's the advanced civilizations before us. My own personal opinion, I think that it's very unlikely that there was an advanced, at least human civilization, at least in the past several tens of millions of years, because of the fact we've stripped all the easy to find ores from the surface. So a lot of the really pretty rocks, so like copper ore, sometimes called one of the types of copper ore is called azurite. It's blue and beautiful. It's a really pretty rock. But you find it around riverbeds and also surface river water, and it's all gone. We've got all the easy rocks. So it's unlikely that because of that, unless we had an advanced civilization that never made metals, which I think is unlikely, right? We're the most advanced, for at least in this planet, since before the dinosaurs. If the dinosaurs were intelligent, I don't know. But okay, so this is how we get metal from ore, and most metal from ore is made in the following fashion. We make a lot of iron. So take iron ore, and we throw it in plus lime, calcium oxide, and plus carbon, and you put it into a blast furnace. What's a blast furnace? You blast oxygen into it. And then what happens is you get some stuff that floats on the surface. The stuff that floats on the surface is known as slag. So you've heard the term slag before. Slag is the stuff that floats on the surface. And then in on the bottom, you get liquid iron, or whatever metal it is you have, copper, lead, whatever it is you're purifying. And then typically, at least, you can form bars from the liquid iron. Does anybody know what pure iron is also referred to as? It's been called pig iron. Do you know why it's called pig iron? It's a farmer's metaphor. So Industrial Revolution came along. Most of the people on Earth, at least half of the people on Earth, were geared directly towards food production. So right now, in the developed countries, it's about 5%. So about 5% are geared towards food production. Right, back before Industrial Revolution, it was 50%. So our types of jobs and what we do have completely changed since then. And on the farm, so humans, of course, we only have 2 nipples, right? So other animals, so if you see cats, dogs, and pigs, they have a series of nipples along their abdomen, and they also have very large litters, and they have the litters, they all suckle along the side of the mother. And when the farmers came from the farm and started seeing the iron and seeing these bars of iron falling, the red hot iron falling off, and pigs are kind of pinkish colored, they said, oh, that looks like a bunch of pigs suckling on its mama. And that's where the term pig iron came from. So it's a farmer's metaphor. So if you hear someone say pig iron, it means pure iron. And we generate quite a bit of iron, of course. And the slag, the impurities, these are typically magnesium and calcium silicates. So silicon, oxygen, calcium, and magnesium. And that's what a large amount of the crust of the Earth is made of. So the answer. So one of the things with this question is, why aren't we getting 100% from this? Because ore is a rock. It's a rock you get from the ground, and it's not a pure rock. It's got other stuff in it. So the impurities, we typically say, we call it slag. Have you ever seen the movies where you have someone making a sword or a blacksmith or something like that? They take the iron out and they're whacking the piece of iron with a hammer and sparks are flying everywhere. That's one way to get rid of the slag, get rid of the impurities. You can hammer them out. Of course, blast furnace is much more efficient, and it works very, very well. So this is how we get all the metals that we use, with the exception of aluminum, gold, platinum, and then the side products from platinum. So palladium and rhodium, for instance, ruthenium, a lot of these metals, they're actually from platinum production, but there's impurities in the platinum. The way we make aluminum, we have two minerals, bauxite and cryolite. So bauxite is aluminum oxide, cryolite is aluminum fluoride. And then you mix that with electricity and carbon, you get aluminum metal. So you can make aluminum with electricity. Gold, there's a couple ways you can get it. You can just find gold. That's one way you can do it. A lot of times, like in riverbeds, there's a lot of gold in the mud. So you can take the mud from a riverbed, and they do this in the Amazon, unfortunately. You can pour mercury metal into the mud, and then you can collect the mercury, and then you can blow out. You can take a blowtorch to it, and you can evaporate off all the mercury, and you're left with gold. And that, of course, pollutes the heck out of the places. So the Amazon has been really polluted with mercury because of that way of mining gold. The way we do it in the United States is we get microscopic amounts of gold in rocks. We grind them down and wash them. Gold's heavy, and just by gravity it settles. We get this really rich sort of mud, and then rich is in gold. Then we put cyanide into it, and the cyanide dissolves the gold out. And then we take the cyanide and we reduce it to get the gold out. Same thing we do with platinum, but platinum also, cyanide will leach out the other metals, so that's how we get things like osmium and palladium and rhodium and other kind of metals, is from the byproducts from platinum. We don't directly mine them, but we get them byproducts from platinum. But this is how we get metals, and metallurgy is very important to us, obviously. We make a lot of iron, and we make a lot of other metals too. Okay, so we have this equation here. So when 28.6 kilograms of carbon reacts with 88.2 kilograms of titanium dioxide, 42.8 kilograms of titanium is produced. What is eliminating reagent, theoretical yield, and percent yield? So let's look at the quantities. 88.2 kilograms making 42.8 kilograms of product. That's not a lot. Okay, so this is not, it's not a little either. This is something called a pilot plant. So what's a pilot plant? Have you ever made cookies at home? Like, I've made cookies at home. It's kind of fun. You have a mixing bowl, you put in the ingredients, you stir it up, and then you take a little ball of cookies and you put it on a sheet, you put it in the oven, it comes out of the oven, you put more on there, and you keep on going until you have all the cookies that you made. Is that how Kraft makes cookies? Do they make them? No. It's an automated process. You have this big mixing tank that mixes up, that makes a slurry. Then you have a machine that kind of puts little plugs of things on a sheet. Then you have a conveyor belt that goes over a heating lamp, and then that cooks the cookies over the heating lamp, and then it falls down and goes into a channel, and they box it up, and they package it up and ship it on out, right? It's a different process than the batch that you make at home, and using a mixing bowl in your oven. So let's say that you're working you're a chemist cook, and you're making different designs for cookies. Maybe you're working for the Girl Scouts or something like that. I love those Girl Scout cookies, they're awesome. But like you're making new cookies, and suddenly now you have to figure out, how am I going to make 5 million, I don't know, frosted lemon cookies? I can make them in my kitchen. I've made a bunch in my kitchen. I've perfected the recipe. Everyone likes it. We decided we're going to have this recipe do it, but how are we going to make millions of these cookies? Well, if I went from my kitchen to mass production, I mean, what's going to happen? I'm going to mess up. I'm going to heat it too long. I'm going to burn some cookies, and doing so, burning cookies, that's a lot of raw materials I'm messing up. That's a lot of burnt cookies I have to dispose of now. That's a lot of money wasted right there. So what am I going to do? I'm going to have a medium-sized plant that's automated, that is called a pilot plant. So I perfect my process on the pilot plant that way, and then when I scale it up even more, I'm still going to make mistakes, but there's going to be much fewer mistakes from doing everything in the pilot plant. So another place you want to see a pilot plant, like if you go to the Krispy Kreme here on Island, they have a pilot plant there. That's when they have the automated system that makes their donuts. That's a pilot plant. So this is what this is, a pilot plant. And pilot plants are important because, say you make a new drug. Say we have some sort of, like, we found an antibiotic that MRSA, it just wipes MRSA out. So we want to get rid of MRSA. We have a new antibiotic, and now we've made this antibiotic in the laboratory, and MRSA is a big problem, so we want to mass produce it quickly. We're going to have a pilot plant to figure out how to make it in large quantities, at least from the laboratory, because in the laboratory it's just like your kitchen. It's really small batches, and you do things very carefully. So scaling up is a completely different process. So make all the mistakes there and scale it up, and now we have a drug that will be resistant to MRSA. We'll see. We have some drugs. It's not MRSA is not incurable. We have some drugs that MRSA responds to, but antibacterial resistance is a huge problem, and it could become a bigger problem in the future. But anyways, okay, so hopefully you understand the whole idea of pilot plant and that kind of thing. So, okay, so let's do this problem. And it's a limiting reagent problem. We have two reactants here. We have, let me change colors, I like blue better. We have 28.6 kilograms of carbon, and we have 88.2 kilograms of titanium dioxide. Oh, and the other thing, percent yield is your actual yield over your theoretical yield times 100. Okay, so let me zoom in on this, and I'm going to cheat looking good. That's where is the book? Okay, here we go. All right, so for the kilograms of carbon, what are we gonna do? We gotta change to grams. 1,000 grams carbon to kilogram carbon. Mole carbon to 12.01 grams of carbon. I'd probably just use 12. And then now the next step is there is mole titanium to 2 moles carbon. I'm getting that from here. So 2 carbon to 1 mole titanium. And then just look in the periodic table. What is molecular? So titanium is 47.87 grams titanium per mole titanium. Where am I getting that number from? I'm getting that from the periodic table. I know you can't see this, but it says titanium. And at the bottom, this is 47.9, but I guess the one in the book is 47.87. So it's this bottom number on the periodic table for titanium. Same thing with carbon. It's 12.01 there for carbon. Okay, and then, I guess one more step. Kilogram titanium to 1,000 grams titanium. And same thing for the titanium dioxide. So 1,000 grams titanium dioxide to kilogram titanium dioxide, mole TiO2, and titanium dioxide is 79.87. 79.87. And this 79.87, that's the 47.87 for titanium plus O2 plus 32. So plus 2 times 16 gives you 79.87. Then the next one is there is mole of titanium to mole of titanium dioxide. Remember, this is a 1-to-1. This one is a 1-to-2. So again, look to the balanced chemical equation to get the right conversion there. And then 47.87 grams titanium to mole titanium, and then kilogram titanium to 1,000 grams titanium. And notice, of course, the thousands cancel. So if you do this, what advertisements I'm going to get today? Let's see here. 28.6 by 12 divided by 2
Are you going back to grams?
times. Yeah, I'm going to kilograms. So this is 57.0 kilograms titanium. Then 88.2 divided by 79.87 times 47.87. And you get 52.9. Okay, so which one do you pick? You pick the 52, it's the lower one. So this is the limiting reagent, and our percent yield is our actual yield. It's given to us 42.8 all over 52.9, and this is equal to 80.9% yield, and that is the answer here. So we have, so it's asking for the theoretical yield and the percent yield. So we've done the theoretical yield before, and from this we've got the lower one, 52.9, and the percent yield The new concept is this is the actual over the theoretical. So we actually get, what's given to us is 42.8, and our theoretical yield we calculate is 52.9. This divided by that times 100 is 80.9%. So recap for this one. Given 28.6 kilograms of carbon, 88.2 kilograms of titanium dioxide, got to find the limiting reagent, and given the fact that we get 42.8 kilograms of product, what is the percent yield? We figure out that the limiting reagent is titanium dioxide. We get 52.9 kilograms of titanium from that theoretical yield, and then we divide the actual by the theoretical to get 80.9%
So
percent yield.
did we decide that the limiting reagent was the TiO2?
Yes.
Because the 52.9 was closer to the actual yield?
52.9 is lower than 57.
Oh,
You pick it because it's the lowest.
oh, I misunderstood this one.
But you bring up some interesting points. Let's talk about actual yield. So why do you not get 100%? And I mentioned this before. Because there's stuff in it. It's a rock. It's going to have dirt. It's going to have other minerals. It's going to have other metals in it. It's not pure. So that's why you don't get the complete yield. Besides the fact you have a chemical process. You probably find this out in lab. You're not getting, like if you're mixing something in the beaker, you're not going to get every single little drop of water out of that. There's something stuck in the beaker. So same thing in an industrial process. You have a leak here, some stuff flies out of the container here, you're getting waste that way, so you're not going to get to 100%. A few cases, you can get over 100% though. So this is usually in lab when you make a precipitate and you don't dry it out. So it makes me think of my football coach. So you got to give 110%. You can give 110% in chem lab if you do not dry your sample. So let's say you have a wet sample and then you weigh it to see what get your actual yield, theoretical yield, the actual yield, you weigh it, and you kind of like, oh, I got 110% this lab. Go tell my football coach, he'd be very proud of you. But of course, what happens is you didn't dry it off enough. So if you dry it off, you can only get 100%. Okay, so let's say you are the plant manager. You are in charge of this plant. You're the owner of the company. You're the owner of a proud company that makes titanium. And this is your engineer, and your engineer goes and shows you, this is what I've done, this is my pilot plant. Are you happy with the engineer's work, or are you upset with the engineer's work? Is this good work or is this bad work? This is really good work. If I were the plant manager, if I were the owner, I would give the guy a bonus and take him out to lunch, or her. So,
Oh, nice. What a
I got two sisters that are engineers.
Yeah, that's nice.
So
Appreciate that.
So why am I so happy? Well, because the limiting reagent is titanium dioxide, and the excess material is carbon. So what do you think is cheaper, carbon or ore? Carbon is way cheaper. Carbon's just coal. It's just purified coal. Carbon's cheap. Ores are expensive. So my engineer made sure that the limiting reagent was the expensive stuff. And so the engineer also put an extra amount of carbon in there, but it's not a huge amount. So I mean, look, this would make 57 and we get a yield of 53. So it's not like, oh, we're just putting tons and tons of carbon in there, why not? There's extra carbon in there because it's cheap, and we want to make sure that the more valuable reactant is not wasted. But then again, the engineer is still being conscious not to put too much in there. So no, this engineer is doing a great job. And besides, also 80% yield, that's pretty good. For many chemical reactions, to get 80% yield is really, really good. So it depends on which reaction it is, of course. But no, I'd be happy. If this was my plant, that person's getting a raise. So, questions with this though? Okay. Last one here. We have 50 grams of oxygen and 850 grams of hydrogen react to make, even though I can't write, to make 50 grams of water. What's the percent yield? So first of all, what's the limiting reagent? Is it going to be oxygen or hydrogen? It's oxygen, yeah. So makes it simple, that's an excess. So O2 is the limiting reagent. So you're giving you 50 grams of water, so you got to calculate the theoretical yield and then divide it by the, 50 grams, the actual yield divided by that theoretical yield that you calculate. So is anyone stuck? No, I'm just starting off. It's really not just needs a
So, you know, this one,
It's really just the other one. I can do it quickly because it's. So where are you getting the 850? You don't get the food done this way.
this is a completely different problem.
Yeah.
So, in this problem, since the Z is a small
18, and it's
number,
very
you move that.
Technically, if we didn't know this before, you would do
18 grams.
find the theoretical yield.
18 grams gives you a mole on the bottom.
And then you would find the theoretical yield using hydrogen.
Yes.
So here we
18 grams of water
use
becomes mole water.
we got theoretical yield using hydrogen. And then this
So you
But this is a different problem.
it's just the same
grams of oxygen. Oh, you have to flip this.
So here's where we go to. idea, this, if you find theoretical negative SEH2, this ratio, if you look here,
So the grams are in the top, you can numerator, and then the grams oxygen in the denominator, so that way you start with units cancel. And then the moles of oxygen, this is multiplied by one. So a mole of oxygen is 32 grams of oxygen. I got rid of the mole of oxygen, so then it's just 2 to 1 ratio. So I'm just going off the way that O2 should add. It's at the units.
So generic create unlimited reagent anyways,
This,
so
yeah.
smaller numbers.
So that way the units all cancel.
yeah, but sometimes it might work out to maybe one mass is really huge or something.
Okay.
If
Let me
we
ask.
were to,
Hang on. I gotta spit this gum out.
Easy when I do that.
but, so, if this were a repeating problem, I would find the theoretical you're using this much H2, and then find the theoretical you're using that much O2. And then we draw the one smaller here.
Am I?
And you find the
I don't know. I can't read your mind.
This.
Did this look right?
You don't need to, I mean,
But shouldn't
that's,
it just be the smaller number if they give you two numbers?
this is right.
Like you're looking at 50 grams
Here,
O2
here,
and
here,
50 grams H2 and you
It's
just go with the
2 moles of
smaller
water and
number.
moles of oxygen.
Yeah, but you have to be careful with that because sometimes
It's the same as the previous problem.
Okay.
It's just half of it.
to be safe.
Before it had 100 grams, you had 112.5. So it's 50 grams. And the units are the same.
Yeah,
except
ask
for
them.
how magnitude is starting.
You have to find out which one is smaller.
I just get screwed.
Yeah.
Because it may not necessarily.
This is where moles of water to,
Over this
you got the moles reactant, then you gotta go to moles product. And then mass product. Alright. It's 3, 2, 1. Oh, it's 2. There's a 2. No, it's not. That'll give you the correctly. Yeah, that'll give you grams of water. Yeah. So that's 56. So you get 50. So your actual yield. So your percent yield is your actual yield of your theoretical yield. So it's 50 divided by that 56. Yeah. Just percent, yeah, the grams, you're just left with that, you're just left with that. You're right. You're the right answer. No, you did this properly. Everything's proper. That's right. Whatever you didn't understand, you did it perfectly. Are you stuck in a certain step though, or are you just? Okay, good. Well, you are getting used to it, so you're doing fine. Have you had chemistry before? Yeah. Okay, so this will be easy. No, you're cool. No worries. Do whatever you want. Question.
For this 50 grams of 2 and 50 grams of H2, would you just pick the small number every time?
This one, since you've had experience with it, I was trying to say that this is obvious that it's reagent.
Usually they have to logic.
So you're always saying no.
Do you have any other questions? Or
No. I don't know why I thought I asked.
oh, yeah, there.
I got it.
I found this one.
It's, oh, well, it's, I was trying to say it's a huge success. I was just commenting that that's. Yeah. Let me move it 70%. It's, should get. Oh, so you didn't do this one there. Oh, which? Okay, where you lost. It would be there, it's water, so there's no one. It would be grams. Oh, you're starting 50 grams oxygen, mold. That right there, okay. 2 mole H2O. Yeah, because you want the, you want the yield in the product. So 2 mole H2O, 2 mole 2, and then it would be 18 grams to. You're doing the right ratio, but that's what you do with the reactor. Yeah, and then you'll get 56. The idea is with the 850, this is just huge excess. So it's, yeah, you need that oxygen. You get, and since you the previous problem, you with 100 grams, you know the oxygen is looking. So, I mean, you can do it. You get 7,650. So you get 56 grams, which is 7,650 grams. So that percent yield is your actual, your theory running. So 50 grams is 6.5. Well, I mean, this is just, I didn't do the proper sequence on this. Are you following? Okay. Yeah. I mean, in this one, yeah, but I'll also give it to you. Looks like yeah. So you just look at your work. You guys got any questions? Okay. All right, so everyone seems to be converging, and the answer is B. So, and again, the reason why I'm doing this is called a formative assessment. And teacher theory formative is on the fly, so I'm asking you, do you understand this as you're learning it? And then I'm trying to correct any mistakes that you or anything you don't understand at the moment. Tests are done as summative, so that's after the fact. Now that you've learned it, I'm going to test you. That's what tests are. They're summative. This is a formative assessment on the fly. Okay, so I have planned for this. So once again, we are faster than the morning session. And I have prepared for this by having additional problems to solve.
Yeah. That's not what I thought you were going to say with that.
Oh, come on. You get extra. You get extra learning.
That's probably you said.
You've done like three problems.
Okay, so now we're looking at some of the stuff, and this is the end of the chapter problems. Calculate how many moles of nitrogen dioxide form when each quantity of reactant completely reacts. So I'm going to look at part C, and I'm going to have you do part D. So part C, 15.2 grams N2O5. So we start off with our given information. So we start off, we have 15.2 grams of N2O5, and we're looking at the moles. We want to know moles of NO2. So we got to do the molecular weight. So 2 times 14 for nitrogen plus 5 times 16 for oxygen. That I can't do in my head. It's going to be close to 100-ish. I know, but let's see here. 28 plus 16 times 5. 108. So mole N2O5 to 108 grams of N2O5. So it's 108. So then the next thing is we have to look to the ratios between N2O5 and NO2. So then this is 4 moles NO2 to 2 moles N2O5. I would normally, if I was doing myself, I would write it as 2 to 1, but I'm trying to limit the confusion for you, the students, in that. And then 15.2 divided by 108 times 2. And we get 0.2, let me see, 281 moles of NO2. All right, so this is your turn. I want you to do this one. And we can do it grams. So 2.87 grams N2O5. All right. So have at it, and so of course putting these numbers in your calculator is a skill. It's called a psychomotor skill. Psycho, your brain, motor, motion, your hands. So it is important that you do these skills. It is not obvious.
Oh, well, we don't need this. We
I'm
don't need
done with it.
Is anyone stuck? Need more time? I went through and wrote them on there. I got 0.0531. Okay, so the next. Okay. Find the limiting reagent for each initial amount of reactants. So we have 2 sodium plus bromine makes 2 sodium bromide. So I'll do B and I'll have you do D. So starting off with 1.8 moles of sodium and 1.4 moles of bromine. Well, before we do this, which one do you think it is? I think it's probably sodium as the main reagent because you double it, because you would need twice as much sodium as you need bromine, and then you have nowhere near that. So I'm expecting it to be sodium. But anyways, I'll do it for both. So 1.8 moles of sodium times 2 moles NaBr to 2 moles sodium. And from this, we get 1.8 moles of sodium bromide. This is an easy one. Let's multiply by 1. We get 1.8 moles NaBr. The next one is we have 1.4 moles bromine. And then we have 2 moles NaBr to 1 mole bromine. So this means we get 2.8 moles NaBr. And which one is the limiting reagent? It is the sodium, as guessed.
Why did you choose B and D? Or why is there a tick mark next to B and D?
Because those look like they'd be the hardest. Would you rather do C?
No.
All right, your guys' turn for D then.
So are they just giving you, like, are you supposed to choose one of those 4, or is the answer one of those 4?
Just find the limiting reagent for each amount of the reactant. So you have to pick which one is the limiting.
Okay,
So
it's different parts.
so starting out, yeah. So it's either for part B, it's either 1.8 moles of sodium or 1.4 moles bromine. And from this, it's going to be sodium. Because you calculate out what the amount of product is for each. You can do them all, actually. Do you guys like puzzles? I like puzzles. I don't necessarily, except for puzzle you assemble. Those are a pain. But I think puzzles are fun. I mean, if you think of this as a puzzle to be solved, then it's more fun. If you think of it as like chemistry and math, you're like, you know, chemistry and that's not as much fun, but puzzles, once you get the hang of it. Right, this is a long way to do it. So I just started out doing B, and this is a long way to do it. But once you get the ratio, like, oh, you have to have twice as much sodium as you have bromine, then once you get that in mind, well, if they have the same of both, the sodium's linear reagent, that, and 6.9 times 2, that's going to be 13.8. And 13.8 versus 12.6, so 12.6 is still lower, so that's that one. And then double the bromine, it'd be 2 moles, and that's more than 2 moles, so it's this one. So once you get the hang of it, it becomes a puzzle to be solved, not necessarily a bunch of drudgery math to do. Well, I don't like drudgery math. I don't know how you guys feel. Some people love it. I know some people get excited about that kind of stuff. But so that's cool, Alan. You just you can get a tire rule. So questions? Is this helping you guys and watching me do more problems? Okay. So it's always easier when the teacher does it. Okay. Okay, 2 problems here. First one here, magnesium oxide can be made by heating magnesium metal in the presence of oxygen. The balance equation of this reaction is 2 magnesium plus oxygen makes 2 magnesium oxides. When 10.1 grams of magnesium reacts with 10.5 grams of oxygen, 11.9 of magnesium oxide is collected. Determine the linear reagent theoretical yield and percent yield for the reaction. So it's similar to the one we did before with the titanium dioxide. So magnesium, I think it's 24. What is magnesium? Magnesium, 24.31. Okay. So we have to look to our periodic table. And, you know what, maybe I'll crop this one out. I'll do this one. So we have, okay. So we have the 2 reactants, 10.1 grams of magnesium and 10.5 grams of oxygen. Magnesium, just straight from the periodic table, is mole magnesium to 24.31 grams magnesium. And now we have to have, so 2 moles magnesium oxide to 2 moles magnesium. Then we're going to get mass. Magnesium oxide, it's going to be 24.31 plus 16 for oxygen. So that's going to be 40.31 grams magnesium oxide per mole magnesium oxide. So, okay, we do that and then set it up for oxygen. 10.5 grams oxygen, mole O2 to 32 grams O2. Then there are 2 moles magnesium oxide per mole O2, and I'm getting that from the balanced chemical equation. It's still the same, 40.31 grams magnesium oxide to mole magnesium oxide. So which one is it going to be? It's hard to say. I think it's probably magnesium, but we'll see. So 10.1 divided by 24.31 times 40.31, and we get 16.7 grams magnesium oxide. Then the next one, 10.5 divided by 32 times 2 times 40.31. Oop, jeez. I put the wrong button on the calculator. And this is 26.5. Okay, which one's the limiting reagent? It's the magnesium. The theoretical yield is 16.7, and we do the percent yield. Percent yield is going to be 11.9 divided by 16.7. So 11.9 divided by 16.7, and that is 71.3%. So magnesium is our limiting reagent. Our theoretical yield is 16.7 grams magnesium oxide, and then our percent yield is actual over theoretical, or 71.3%. So does everybody get this one? Questions on how to do this? Okay. And in that case, last problem for you. Urea is a common fertilizer synthesized by the reaction of ammonia with carbon dioxide. So 2 ammonias plus carbon dioxide makes urea and water. Industrial synthesis of urea, a chemist combines 136.4 kilograms of ammonia with 211.4 kilograms of carbon dioxide, obtains 168.4 kilograms of urea. Determine the limiting reagent, theoretical yield, and percent yield for the reaction. Oh geez, we're about almost out of time.
Homework.
I don't know if we have time to add
No.
all that.
No, we don't. Okay, so you're saved by the bell then.
You could probably do
So, okay. Don't have enough time to finish it in 2, unless you can fill it in 2 minutes. Can you?
Actually, all you need to know is that there's
Okay.
168.
So I'll see you guys on Wednesday, and we'll jump into chapter 5.
You need all of that, right? I'm gonna write it down.
You want to do it?
Yeah, we leave that up for a second.
Okay, let me stop the recording.
Ammonia's H2.
Yeah.